Hello and welcome to a short UCL physics video that gives an overview about what the cosmological constant is and how it is used to describe our universe. This video is meant to supplement the second half of the Atom, Stars and the Universe module, taught in the first year undergraduate physics course at UCL. In order to understand the existence of the cosmological constant, we must go back in time. In 1687, Sir Isaac Newton published his book called Principia Mathematica, which laid out some of his groundbreaking work on the laws of motion, law of universal gravitation, and much more. Amongst these subjects, it also talked about the Newtonian universe, where he believed that the universe was static and infinite. Fast forward to 1915, Albert Einstein formulated his general theory of relativity, but according to his calculations, the universe had to be either expanding or contracting. As the accepted view at the time was that the universe was static, Einstein introduced the cosmological constant lambda into his equations to counteract the effects of gravity so that the universe would remain stable. Thus, with these calculations, he published his book titled Relativity, the Special and the General Theory in 1916 to explain the Einsteinian universe model. However, shortly a few years later, in 1929, Edwin Hubble's paper on the Hubble law and the expanding universe changed everyone's understanding of the universe. This discovery then led to Einstein abandoning his constant and calling it the greatest blunder of his life. Finally, in 1998, using data from the redshift of type Ia supernovae, the Supernova Cosmology project revealed that the universe was accelerating and revived the cosmological constant that was previously dismissed by Einstein. Today, this constant is used to describe some advanced notions in cosmology, such as dark energy and dark matter, which we'll go into the details of now.
The density parameter. This is something we covered in ASU last year and is defined as the ratio between the density of all mass and energy in the universe and the universe's critical density. The relation between these terms actually defines the ultimate fate of the universe, where, if the ratio is less than 1, where the universe has less than critical density, then the universe lacks the total mass required to overcome the current rate of expansion through gravitation, and will continue to expand forever. This is known as the open universe. If the ratio is equal to 1, the universe has enough mass to halt current expansion through gravitation, but it will do only just that. Expansion will halt, but nothing will expand or collapse afterwards. This is the critical density of the universe. If the ratio is greater than 1, the universe has enough mass to halt its expansion and also collapse in on itself, resulting in a big crunch. This is the closed universe. But how do we calculate this density parameter? We do this through adding up three component densities: the density for baryonic matter, or normal matter, omega b, the density for dark matter, omega d, and the density for dark energy, omega lambda. Notice how the symbol for dark energy used here is the same as Einstein's cosmological constant. Research done in 2015 by the Planck Cosmology probe has shown that the regular matter accounts for only 4% of the universe's total mass and energy, where the rest is made up of dark matter at 22% and dark energy at 74%. So we know that dark matter and dark energy makes up the majority of the universe's energy and mass. But how does this relate to the cosmological constant? As explained in the introduction, Einstein originally introduced the constant because in his calculations, he found that the universe was either expanding or contracting. To align with the general consensus of the time that the universe was static, he introduced the constant as a repulsive force holding the universe together. Fast forward to 1998, the universe was actually found to be accelerating its expansion due to some unobserved forces we now call dark energy and matter. To explain this, the cosmological constant was reintroduced, again as the repulsion caused by dark matter, where this time instead of holding the universe together, it causes the universe to expand. As an homage to Einstein, the lambda symbol is now used to represent dark matter in equations.
Einstein confessed that his introduction of the cosmological constant was his greatest blunder, but years later it was reintroduced, and today it explains dark energy, which makes up 70% of our universe. However, a fundamental problem remains. The theory of quantum mechanics and the theory of general relativity cannot agree on the value of the cosmological constant. The theory of quantum mechanics states that in a vacuum, virtual particles pop in and out of existence, creating energy. When physicists attempted to calculate its contribution to the cosmological constant, the prediction varied by a factor of 10 to the 121 to the observed value. This is described as the worst theoretical prediction in the history of physics. This discrepancy means the two theories remain separate. A key to resolving this problem is to collect more data from across the universe